Okay, so now what I'm going to do is give a very high-level conceptual overview of what in engineering is known as Euler-Bernoulli beam theory. Um, this will be very high level. I'll put in a few equations for the kinds of people who may have engineering backgrounds and might want to see how this ties into what they've learned in school, but those can be ignored by people who aren't interested in that sort of thing. Um, so let's get started. A lot of the concepts I'm going to discuss later can be kind of thought conceptually as a form of bending, or pure bending is what I'm calling it here. Um, Pure bending is what occurs when you apply moments to a beam-like structure. So here's an example. I have this piece of foam, and I apply moments to each end of this beam, and it assumes this deflected shape. Now when I say moments, that's the term that's typically used in engineering. The word torque is accurate as well. Um, it's also worth noting that you never really get a beam that's in pure bending. It's kind of a theoretical concept, but you don't have to worry about that too much right now. Anytime you were to apply a load, for instance, if you were to apply a force here on the beam, there would be some bending stresses induced in the beam. And what we're going to talk about is going to give you a conceptual idea of what happens when you apply that load. So if you look at the beam, what's important to note is let's look at the deformed shape. So if you look here, this material on the top, it all has to elongate or stretch in order to assume this deformed shape. So the distance from here to here on this upper surface is longer than from here to here on the undeformed shape. And if you look at the bottom part of the beam, all this material has been smashed together. So we'd say that's in compression. All this material had to shrink to assume this shape. So what we say is all the material down here is in compression, and all the material on the upper half of the beam is in tension. Now if you can kind of think, if the material on top is stretching, the material on bottom is compressing, there's going to be a point somewhere in the middle where actually the material is neither stretching nor compressing, and that's what we call the neutral axis, and I'll talk about that a little bit more in the next slide. So you can also think, for people who might have an engineering background, if you think about it, this has a certain radius of curvature associated with it, and you can see the circle up here on the top is going to have a larger radius of curvature, or I guess a larger radius of curvature, whereas the material here on the bottom, this has a smaller radius of curvature, and that's why this is compressed and this is stretched. And an example of a beam that might experience this in your day-to-day life is something like a 2x10 here that might have a load applied to it. It won't be in pure bending. If I was to apply a force in this direction, it wouldn't be in pure bending, but it would experience bending stresses. So now what we're going to do is look a little bit at how the stresses in a beam are distributed under pure bending. So what I've done here is I've gone ahead and put this dashed line here, and this indicates the neutral axis of the beam, and that is the part of the beam that experiences neither tension or compression. It's the material there is at more or less its same length. Well, it is its same length theoretically. And if you want to learn more about the neutral axis and how some of these kinds of concepts are defined, you can look in any common solid mechanics book. Look up Euler-Bernoulli beam theory. Here's a good reference right here. And so if you look in here, you can find the expression for how the longitudinal stresses, and that's stresses in this x direction or along the axis of the beam, are distributed throughout the beam. So what we have here is m is the moment that's applied, the magnitude of the moment. Y is the distance from the neutral axis, so this distance right here. And I is something called the area moment of inertia, and I'll talk about that a little bit more in a moment here. But you can see if the m is constant and I is constant, as we get farther away from the neutral axis, we get higher and higher stresses. So you can see when you're out here at the furthest distance from the neutral axis, this is where the highest stresses occur in tension. And conversely, if you go down the other direction, the opposite surface is where the highest stresses in compression occur. So what I want to do now is talk a little bit more about that area moment of inertia term, the I that was on the bottom there, because it's kind of important. So, since I is in the denominator, what you want typically is an I that is very large, so that for a given applied moment you have lower stresses in the beam. And the lower the stresses are, typically the lower the strains your structure will see, and in turn the smaller the deformations of your structure are going to be. So typically you want to have a high moment of inertia. And so this is actually the expression for the definition of the moment of inertia. And you can see there's some calculus here, but you can really kind of replace this integral sign with a summation and just think of it this way. So first, we talk a little bit about the neutral axis. The neutral axis, I'm not going to go into the details, but it's basically at the centroid of the beam. That's basically the you can kind of think of it as the middle of the beam. I'm not going to go into the details of what that is. You can look in a textbook if you want to learn more about it. But you can roughly think of, if you have a symmetric beam like this, it's going to basically be in the center of that beam. Now, you can see we have this y squared term and a dA term. So the dA term just indicates a small portion of area, and the y is the distance that area is from the neutral axis. And you just add a whole bunch of these little sums up, and you get the composite area moment of inertia. So what ends up happening is that as you get farther away from this neutral axis, this material out here, you can see there's a y squared, it contributes a lot to the overall area moment of inertia. Whereas material that might be really close to the neutral axis, the y squared term is going to be very small, and so you're not going to get as much contribution to the area moment of inertia. And that is why when you look at I-beams or things like this channel here, you'll see a lot of material far away from the center of the beam. And that's because by adding a little bit of material far away from the center of the beam, they're significantly increasing the area moment of inertia, but it's not taking as much material, which would cost more money, and it's not taking as much material that would add weight. And so you're getting a structure that's lighter and cheaper and still has good stiffness properties. And this is also part of the reason you'll see your 2x4s oriented in this direction as opposed to flat, like when you're looking under the joists of your house or underneath your porch. In some sense, you can kind of think of this area moment of inertia, the taller your beam is in the direction of the applied load, the stiffer it's going to be. So once again, just real quick to hammer the point home, you're going to think this is your 2x4, maybe you apply a load. Now if you were to look at both of these cases, this orientation of your dimensional lumber is going to be less stiff. This is going to tend to deflect more for the same load as this beam here. And it's kind of this taller equals more stiffness point of view. This effectively has a low area moment of inertia, and this has a high area moment of inertia relative to this. So that's kind of the background. I'm going to stop there, and in the next slide, in the next part of the presentation, we're going to start looking at the barbecue. Thanks. Bye.